Good. Sorry. Okay. Hello. Hello. Good morning. Good morning. I'm messed up on an audio thing. Good morning, Alyssa. Thank you for saying so. Good morning, Vivian. Good morning, Lakshmi. Good morning, Soad. Good morning, Noel. Good morning, Jayla. And they say yes, Vivian, Alyssa, Noel, Charlie. Oh, good morning, Charlie. Good morning. Thank you. Awesome. Good morning, Lakshmi. Good morning. Did I say Lakshmi? Yes. Good morning, Farouk. Good morning. Oh, thank you. Good morning, Charlie. All right, double morning, Charlie. Good morning. Oh, cool. Oh, wow, cool. No problem. Direct chat person. Got you. No problem. And that's exciting. That's cool. Okay. But nobody knows what I'm talking about because it's such direct chat. Okay. Good morning. Okay. Awesome. Sorry, I started a little bit late. Okay. We are. Okay. We're actually. Oh, that's awesome. Wait, that's not a fish tank behind you, Vivian, is it? Okay, sorry. Wait, Vivian, you don't have a fish. No. Okay. Okay. So we're gonna keep rolling here. The thing that we ended on, well, the thing that we ended on last class is a very big deal. We're going to come back to it a lot in more ways than one, in many ways. We're going to come back to it for the rest of our life. I mean, okay. Let's just get straight to it. Okay, we're going to say over and over and someone's here in all kinds of different ways. And when I say all kinds of different ways, that's coming. Like GPR, anytime I write from here on in, anytime I write GPR, I mean Galileo's principle of relativity. Okay, it comes from like the year 1626 or 1632, depending on which book you're talking about. It comes from the mid-17th century. Galileo's principle of relativity. It is the principle upon which Einstein based his entire special theory of relativity and general theory of relativity, special theory of relativity being published in 1905. Anytime you've ever heard relativity in the context of physics, it ultimately comes back to Galileo. And that's explicitly through the pen of Einstein. I mean, again, let me just say, Einstein didn't plagiarize Galileo or anything like that. Einstein directly quoted and attributed and credited his work to Galileo. And the aspect of Galileo that we're talking about here, whenever we talk about relativity, is Galileo's resolution, or at least approach to the whole question of whether the Earth can or cannot be said to be moving, particularly given the fact that we don't feel it moving and we don't directly sense it moving in any mundane, typical, daily, or any clinical, deliberate, scientific way. We literally don't feel the Earth moving. We literally can't find any data to directly show that the Earth is actually moving through space. But Galileo's ultimate view on this is that you can't ultimately collect any data or experimentally verify whether anything at all is actually moving. Galileo's ultimate point is that it's perfectly conceivable for the Earth to move at, in fact, any kind of crazy high speed that we might want to say, because ultimately velocity is not the sort of thing that we do ever feel, okay? Ultimately, what Galileo says in Galileo advances what we now call a principle of relativity, and he advances it in a number of different ways, okay, in a number of different books, and frankly, in a number of different languages, none of which is English. So we're going to keep saying it in a number of different ways, okay? We have so far advanced 3 forms of this principle, like what we call form number 1, form number 2, form number 3. There are more forms to come, and there's 4 through 7. Or depending on what kind of semester we have, we could even do 2 more. We can go to form number 9. And some of them are explicitly mathematical, and some of them are less mathematical. I mean, so far they haven't sounded very mathematical. The very first form of all of them is that the laws of physics are the same at all constant velocities, right? And again, notice that way of saying it, that first way of saying the principle, perhaps the most original or the most fundamental way of saying the principle, doesn't sound like it's saying anything. It doesn't really sound like it's saying anything interesting or controversial or new at all. But by the time you get to form number 3, where we left yesterday, we're saying that if you really accept that the laws of physics are going to be the same at all constant velocities, that if you really think that through and think its implications through, then you realize in form number 2 that what that means is, okay, if the laws are always the same, no matter what velocity you're at, even if that sounds self-evident or like not even interesting, then you get to form number 2 where you say, well, then that actually means that actually then no matter what velocity we're going, any experiment we would ever do will always end up leading to the same result, right? Again, it seems sort of self-evident. I mean, it seems reasonable and almost seems so reasonable as to like not be that interesting, that any experiment you do, and I mean any experiment you do that's already sort of designed within the confines of your current technology and whatever your current understanding of the laws are, or even any experiment that you might conceive of in some future or more advanced technology, or even under some future more sophisticated set of laws, if you really believe that no matter what the laws are or are ever going to be, as long as you believe they are laws that govern motion, and therefore they should not change from one motion to the next, because again, if they did, then they wouldn't be laws of motion, they would be examples or circumstances of motion, right? So whatever the laws are, as long as you believe they're going to be the same at 0 miles an hour or 30 miles an hour or 100,000 miles an hour, then it follows in form number 2. Again, we wrote this down yesterday. We're not going to write it again now today. But then form number 2 says, well, then any experiment you'd ever do, even ones you haven't thought of yet, would necessarily lead to the same result, whatever speed you're going, right? So the simple example of that is, let's take an experiment that is not that hard, that doesn't require a lot of deep, precise knowledge, just an experiment of I drop a pen, or like I drop any object from my hand with no tricks. I don't throw it, I don't thrust it, And I just drop it. And I ask, where's it going to land? Well, if I'm standing still and I drop something, I would expect it to land directly below my hand. I would expect it to fall in a straight line compared to my body, right? Again, if there's no tricks up my sleeve. Well, according to Galileo, if you expect that when you're standing still, a pen that you drop would land directly below your hand, then you should equally expect that even if you were standing on a moving platform, like through the airport, going through the airport, right? Even if you were on a platform that was going 10 miles an hour, if the laws are the same, if the law of gravity doesn't suddenly change just because you're on a platform, then you would expect that the same thing should happen, even going 10 miles an hour. And if you think about it, it totally does, right? If you're at the airport and you drop something, you don't lose it. It doesn't, the person behind you doesn't pick it up for you, right? Or if you don't believe that or something, or if it seems weird to picture, if you're on a subway and you're sitting still and you drop something, it lands on your lap. It doesn't land on the person behind you, right? Or certainly if you're in an airplane or if you're in an elevator, right? And you drop, if you're in an elevator cruising from not at the beginning, not at the end, but just in the middle of the journey, where everything feels normal. Everything is normal when it feels normal. And if you drop something or you throw something up, you expect to be able to catch it, right? On an airplane, same thing, right? So Galileo says, well, right, of course, any experiment you do at any velocity should work out with the same result. But therefore, if that's true, and if not only true, but almost obviously true or incontrovertibly true, then Galileo says, well, then that means you couldn't do an experiment to find out whether you are actually moving or not, because no matter whether you're moving or not, or no matter what speed you're moving, as long as it is a constant speed, constant direction, right? All of it, the laws are the same at all constant velocity. So as long as you're and velocity means speed and direction. So as long as you are traveling at a constant speed and direction, any experiment you do or even think of is going to work out to the same result. Therefore, I'm still on form number 2 now, and I didn't mean to, I'm just reviewing again. Sorry, I didn't really mean to do this, but what else is new? Then that means that any experiment you do will work out to the same result. Therefore, flip it and realize, oh, that means any experiment I do, it's going to be the same result regardless of what velocity I'm going. Therefore, I can't use the result to tell me what velocity I'm going because it's going to be the same result either way. Therefore, Galileo says in form number 2, therefore, if you ever want to find out what speed you're actually going or what direction you're actually going or whether you're actually going at all or not, you can't do an experiment to find out because all experiments are going to work out the same way. So then Galileo says in form number 3, okay, and again, each time I write, each form is slightly different because it advances our understanding in a different way. And anytime I write a form, I don't always write it in the exact same words because again, he didn't write them in English anyway. I always write them in words. I always try to choose my words so that they capture the meaning. And each time I write it in slightly different words to try to maybe grab some of you who might not have totally caught it the first time. I'm being strict about my words because there's lots of words that wouldn't work, but there is more than one word that works anyway. But that's why I encourage you to keep writing these down as I keep writing them down, because they will sink in more and more deeply as we go. What I'm saying in form number 3 then is, well, if form number 2 said no experiment is ever going to tell us how fast we're moving or whether we're even whether we're moving at 0 or not, or 0 or 100 or 100 or 1,000 or 65,000 miles an hour, then Galileo says, well, then I'm sorry, but if you can't do an experiment to verify, to ascertain whether you're actually moving or not, then I'm sorry, from here on in, I say we can't even coherently talk about whether you're actually moving or not. From here on in, and this is the break, this is the birth of experimental physics as a branch of science. This is where natural philosophy breaks with philosophy in general. It's no longer a head game now. It's not just about what we can conceive or imagine or abstract. That from now on is going to be the province of math or philosophy or religion or whatever, all legitimate provinces, but not the province of science. Science, as as of Galileo, as of the 17th century, what makes science from here on in is that set of claims that is tethered to the reproducible collection of data, right? What makes science is that all of our claims, all of our beliefs ultimately come from and refer back to reproducible methods of collecting data, i.e. experiments, i.e. we don't say anything anymore that can't be verified by somebody else if they follow the same recipe we use to get information from space and time into our heads, right? So is as of number 2, Galileo saying there ain't no experiment that can tell you whether you're actually moving or not. Then number 3, Galileo says, so therefore this idea of actually moving or not, it's not a real idea anymore. It's not meaningful. It's not coherent. We can talk about it, whether you're actually moving or not. We could philosophize about it, but scientifically, we drop it as a fair concept. From here on in, we say velocity is, and so now, okay, again, I'm sorry to keep repeating this, but again, there's no more fundamental idea in physics. Honestly, this is the birth of classical physics right here, is not the equation for velocity, but the recognition that from here on in, velocity is not like temperature and it's not like mass. Velocity from here on in, anytime we use it, from here on in, even when we use velocity in an equation, for example, by the way, when we start getting mathematical again, which we will in like 5 minutes, which I always say, and I probably mean 20, but from here on in, even when we use equations and stuff, whenever we write V for velocity, if we're careful, and from here on in, almost always, we're going to actually put subscripts next to the V. We're never going to just write V. Well, we're very infrequently just going to write V from now on. We're usually going to write something like V sub AB or V sub XY or V sub AC or something. We're always going to write velocity as a comparison between 2 objects, because from here on in physics, velocity is not a property of any single object. Objects don't have velocities from here on in. Objects bear velocities to other objects. Velocity is a comparison between 2 objects. That's the only meaningful way it functions from here on in. That is to say, velocity is relational, or the way we say in contemporary language, velocity is relative from here on in. That does not mean it's approximate. It doesn't mean it's a fictional idea. It doesn't mean it's not accurate or exact. It means that it's not objective. It means that velocity from here on in is necessarily a comparison between 2 objects. And what it means is that if you change one of the objects, you change the number of velocity. It means that from now on in, there is no meaningful answer to the question. I mean, if the question that started all this is, well, okay, like enough, yeah, enough. Can we like get back to physics and just like tell me, does the Earth actually move or not? Like, just tell me. Like, because you like before Galileo, everybody thought the Earth didn't actually move. Before Galileo, everybody thought the Earth actually stood still in the center of the universe. And now you're saying something different. You're saying Galileo is a hero, but he's not a hero in the way you're saying you do like Galileo, but you don't like the way you were taught Galileo. Like, what are you saying, Yaverbaum? I'm saying that according to Galileo, if you ask Galileo, is the Earth actually moving or not? Galileo would say, wrong question. The Earth is not actually doing anything. The Earth is actually moving. The Earth is actually sitting still compared to itself. Relative to itself, the Earth is going 0 miles an hour. My body, relative to the Earth, is going 0 miles an hour. Hence, I don't feel anything interesting. But compared to the sun, the Earth is going 65,000 miles an hour. Compared to the Earth, the sun is going 65,000 miles an hour, right? Compared to the center of the galaxy, the Earth is going 650,000 miles an hour. What is the Earth doing? Depends what you compare it to. That's what we're saying. And we're not saying that as a cop-out. And we're not, and you might even be thinking like, oh, well, that's all you're saying? Like, okay, depends what you're comparing to. Yeah, like I could have told you that. Well, kind of. I mean, I hope so. in a way, I hope I'm saying something that you kind of knew all along. But the strict thing I'm saying, the sort of big news about it, is that what you might have sort of sometimes thought all along, like, well, I guess it's sort of compare. Like if you've sort of all along thought, well, how fast the Earth is going, I guess sort of compare it matters. Maybe it depends on what you compare it to. Like the Earth is not going compared to my feet, but it is going compared to the sun. And it's going even faster compared to the galactic center, I guess. Like if you've kind of always thought that, I'm saying, first of all, good, awesome, yay, because you're correct. But I'm also saying that's the only correct way to think about it. That's not just sort of sometimes true. And that's not just sort of sometimes true because we sort of like can't think of anything smarter to say. It's always true because it's actually the smartest thing to say. It is for all time. What we're saying is literally, you can never talk about velocity coherently other than talking about it that way. We're saying nothing in the universe actually has a velocity. Everything and anything in the universe has a velocity compared to anything and everything else. That at any given moment, if you're talking about any object and you want to know its velocity is, you must specify a frame of reference. You must specify a base of comparison. You must specify a second object. If you want to attribute a velocity to the first object, you cannot attribute velocity ever in physics to a single object. You must only talk about it as a comparison between objects. Bottom line, last thing, or the last two ways to put it, and then I really move on. And this is going to come up again. Everything that we do in physics from here on in, I promise you this, whether you see it or not, everything that we do in physics from here on in classical physics from the 17th century, in contemporary mechanics from the 20th century, in electricity and magnetism from the 19th century, like physics 204, anything we do in physics evolves from this idea and is tethered to this idea, so much so that the truth of the matter is that every seemingly difficult equation or strange like set of details in physics comes so much from this idea that actually you can figure out all the rest of physics on your own if you take this idea super seriously. Like for real, every equation we're ever going to do actually is just another form of this equation, of this crank being turned. I mean, of this statement. For real, for real. And we're going to solve problems with it. Oh, so two things. One, what I'm saying is the word fast or the word speed is really like the word taller or something. If you say how fast is something going, okay, it sounds like a reasonable question. Like, how fast is the car going? Like that sounds like, oh, I don't know, 50 miles an hour. What we're saying in physics from now on is like, no, actually, saying how fast is the car going is like asking how taller is my sister. Like literally, that's what we're saying. Like if I just walk up to you and say, oh, by the way, here's my question. I'm going to show you a photograph, or like I'm going to introduce you to her. Like you'll meet her the other day. Here's my sister. Okay, so here's my question: how taller is she? Like if I said that to you, you'd be like, wait, what? And if I said again, no, like look, really, here she is. Here's my sister, ladies and gentlemen. Or here's a photograph. Like okay, like I'm giving you all the evidence. Like here you go. And I say, so my question is, how taller is she? Like hopefully you'd look at me like I'm crazy. You like wouldn't even be able to. How taller is she? You might like, wait, how tall? No. How taller is my sister? You would hopefully say something like, how taller than who? Like taller than you? Taller than a tree? Like, what do you mean? How taller? Taller than what? Right? If I said how taller is she, you would force me to give you some other thing to compare it to in order to, and otherwise you wouldn't answer the question at all. You'd look at me like I'm crazy. That's what we're saying fast is from now on. There's no such thing as how fast is something. There's only how faster is something. You've got to specify. That's what we're saying, okay? And the last way I'm going to put it, and I'm really going to move on for the moment, is what we're really saying is, Hold on, I'm just gonna close the door. Hold on. Okay. The upshot of the, and again, I can't emphasize enough how much this is going to come up for the rest of physics and how much it affects problem solving and all that. But a tidy way of putting, so I'm saying all velocities are relative. Velocity is always a comparison between two objects. It's never a property of one object. So another way to put that, to bring it all full circle to the Earth or whatnot, or to, again, bring it back to like, this is science, right? This is going to get more and more mathematical. I promise it does get mathematical, but it is science, not math. This is about us interacting with the empirical, external world of space and time. It's about our brains, our minds, collecting information from the outside world and then processing that information. Our minds can do a bunch of really cool things on their own, and we call that math. Like, honestly, like, you can like be a brain in a vat doing math. You can be a person in a jail cell for the rest of your life and do some really serious math, like with no sensory input. And I'm not even joking about, like, math is wonderful that way. But if you want to do science, if you want to do physics, if you want to actually come to conjectures, hypotheses, inferences, analyses, and conclusions that are related to the evidence, related to evidence in the external world of space and time, evidence that comes in through the interface of your five senses, right? Then that's a different ballgame. That's the ballgame of science. And so one way to package all of what I'm saying about velocity is not something that you can ever sense. Velocity is not something that you can get data on. Or certainly not objective velocity, not velocity as a property of an object. We never feel velocity. That's the ultimate, but the reason that we can say the Earth is moving 65,000 miles an hour while we don't feel it is we, in fact, if you really are following what I'm saying, we never feel velocity. Velocity is not the sort of thing to be felt. You cannot feel it. You never have motion sickness. You might think you do. And I'm not saying you never get sick while you're moving, but I'm saying whenever people say like, ooh, I'm getting motion sickness. Ooh, my body doesn't like it when I go fast. Your body doesn't give a crap or no. Like, if your body doesn't like it when you go fast, I'm sorry, you'd be puking all the time, right? You don't feel velocity because you can't, because it's a comparison, right? I mean, but you do feel things. We do feel like we have the sense of motion. So what is it that we're sensing? What is it that we feel when our stomach goes, ah, something's going on? What we feel are changes in velocity, okay? Like, which brings us to the next chapter and the homework assignment that is technically due next Monday that we're going to start going over right now as like an advanced help session or whatever. Okay, we finally, for all that talk, the reward of all of this abstract astronomical talk is we finally get to our next equation. And they're going to start coming a little bit more rapidly now. We're going to start accelerating in this curriculum now, because we've in a way spent all this time trying to end like the key, like physics is a study of motion. We're from a number of various angles, and there's still going to be more. We've kind of tried to unpack like the basic idea of motion. And one aspect of that idea is that actually motion is not like an objective property of any single object. Motion is not actually something that we have any sensory access to, because the laws of physics are all the same as long as the type of motion is kept the same. As long as you're going constantly at 0 miles an hour and constantly to the north, the laws are going to govern you exactly the same way as if you constantly went 5,000 miles an hour to the south. Like that's GPR. But that all presumes constancy. That all assumes that the state of velocity is not changing. What I'm here to say now and move us on forward in the curriculum is what we do actually sense, what our body can, and there's reasons for this that we'll get into, but what our body does experience or what our data can reveal to us is changes in velocity. Right? And you know this, of course, everybody knows this. I mean, and hopefully this is, and we're going to start putting symbolism and mathematical details to things that you've kind of always sensed your whole life in a way. I hope many of you. You might have even thought about this. And if you're like me, I thought about some of these things before I saw them in physics, and kind of when I liked physics, which was not always when I was growing up, but when I liked physics, it was generally because people would start saying things. I was like, oh yeah, I wondered about that, but I like kind of just thought I was in my own world with that. Like I thought that was just like a little game I was playing with my mind. I didn't realize like that was a thing. Well, I'm here to say, yeah, it's totally a thing. It's like a major thing that when the elevator takes off, when it first leaves the low floor and you start going up, that's when you feel it. That's when you freaking know you're in an elevator, right? Or when the airplane takes off, that's when you have to keep your seatbelt fastened. And you know something is going on there and it's not safe. And that's also true when the airplane is slowing down. And it's also true when the airplane is turning or bumping or lurching or whatever, or mopping or squeezing or dusting. And all of those things, when you feel motion, are actually changes in the state of motion known as accelerations. Acceleration is what we actually experience. Acceleration is where the physical action is. And there's reasons for that, one of which is called Newton's second law, which tells us that, in fact, in order for there to be an acceleration, there must be a net force, and forces are interactions between objects. Those are real and we feel them, and we'll get to that. But what I'm saying right now is acceleration is change in velocity. Acceleration is change in velocity. In fact, specifically mathematically, from here equationally, so this is like equation number 2, right? Like this is an actual official equation now, yay. This is an official equation, but notice, just like our other equation, in fact, let me. Just like our other equation, it's nothing more than a definition written in symbolic form. It's not a discovery from a lab, and it's not a like a descriptive empirical result to be accepted on faith or accepted from authority and then memorized. It's simply a defining one term as a shorthand for a set of other terms and then putting them in symbols rather than long English words. It's just a definition, and hopefully, therefore, like an intuitive one, but we can express it as an equation. And it's an equation that looks a heck of a lot like the other equation that we have.
Okay, we have two equations so far in this class now. Each one of them is just a definition written in symbolic form. Each definition has a perfectly parallel structure to the other one. Average, so like on the left side is an average quantity of some kind that applies to a segment or an interval or a region between 2 points in space and time. And then on the right side of each equation is reference to particular points, single points in space and time. So the first equation says the average velocity over some interval of space and time is equal to the change from one position to the next in that interval of time, right? Average velocity is displacement over time, meaning change from one single position to the next single position while the clock ticks from one single instant to the next single instant. Notice again, don't forget, like these really are parallel structures. Like what we're really saying here is this, right? But we're saying, I just really want, as we get more and more equations, I just want you to see it all the time. Physics never, almost rarely, just suddenly just introduces an equation and says, please accept this because we did a bunch of experiments and it seems pretty reasonably right. And even though you weren't there for the experiments, this was the result. So please accept it. Like every next equation in physics is supposed to be a totally acceptable, nearly self-evident step of reasoning to which we all have access. So like, I'm just trying to emphasize that here, but I'm saying, so average velocity is change from one point in space to another point in space as time ticks from one point in time to another point in time, right? It's just the first point in time we almost always just call zero because that's when we start our stopwatch if we're collecting data from an experiment. And then by the same structure of reasoning, of definitional invention, we then say from here on an average acceleration. Remember, the bar over something always means average. Well, like right? So the line over something always means average, and the naught, the subscript zero next to a variable always means the initial value of that variable. That little naught subscript always means the value of that variable at the point where time equals zero, right? Just reminding you. So we're going to continue using that notation and we're using it as we expand things. So we now have this idea that just like average velocity equals the change from one point in space to another as the clock ticks from one point in time to another, average acceleration, we're going to say from now on, is the change in velocity from one point to another as the clock ticks from one point in time to another. Okay, same exact idea, same structure, all that. I'm just looking at the time. Oh, we got plenty of time. Wait, is that right? Oh yeah, we got plenty. That's weird. We're almost getting something done. Almost. Okay, and from now on, you can accept this equation and use it at all times. Oh, and I might add, just like the first equation, you should be aware right from the get-go that if we're really accepting this equation from now on, it works something as an equation, like both sides are equal. So it doesn't matter what order you write it in. It doesn't matter if you read it from left to right or from right to left. And it doesn't matter if you multiply both sides by t or subtract v naught from both or add v naught to both sides. Like you can solve for any variable you want in this second equation, just like you can in the first, because it's just like a truth from here on in. And it is a truth because it's just a definition. We're saying from now on, if you're ever observing the velocity of something change from now to later, and you subtract, you look at the difference between two velocities and you divide by the difference in the time moments, then we're going to call that ratio an average acceleration. Okay, so acceleration Note also, you might want to write this well. One last thing to note too is that at a certain point in this course soon, or in physics or in our lives, we're going to start putting arrows on top of these symbols to constantly remind ourselves, to emphasize that these are now our vector quantities. Remember, average velocity is displacement per time, right? As opposed to the sort of softer, less formal, and certainly less directional quantity of average speed, which was distance over time. Average velocity is displacement over time. Displacement has magnitude and direction, right? Displacement is a vector. Average velocity was the ratio of that vector to time. So average velocity was a vector. And again, you might want to be keeping track of this on a piece of paper or something. You might. But displacement was a vector. Velocity is a vector quantity, meaning it cares about magnitude and direction, meaning velocity can be, at least if we're still dealing in one dimension of space here, velocity could be positive or negative with equal coherence. And now I'm going to say acceleration, same thing. Acceleration is change in velocity per time. And really, you should write this down. That means two things. One, it means acceleration is itself a vector quantity. Acceleration in one dimension of space can be positive or negative. And that has a lot of implications we're going to see in a moment. So acceleration has direction. What was I just going to say about that? Acceleration has direction. It is a vector. Oh, I know the two things I want to say about that. And yes, this is what you really should write down. That means two things. When I say acceleration is a vector, that really means, well, at least two things. I can't emphasize this enough. Let me try to emphasize this more. I really should probably write this on its own page, but acceleration is a vector. So do I want to write this on its own page? Okay. Yeah. I'm just trying to figure out. Okay. Just a couple things to note, and then literally we're going to start applying this numerically, quantitatively to homework 4, which is not due to Monday, which I'll screen share in a second for anybody else tuning in. So first of all, I'm saying, remember, velocity was a vector quantity. Velocity cares about magnitude as well as direction. And acceleration is any change in velocity at all. Like again, acceleration is anything that is not falling under the heading of GPR form number 1. Any kind of change of speed or direction, any kind of change in velocity would constitute an acceleration. And any kind of change in velocity, it turns out, is what we end up feeling, right? So so acceleration in physics doesn't just mean speed up. Acceleration means a speed up or a slowdown or a change in direction, i.e. a turn. Okay, and we don't have different words for that. We might have different symbols like positive acceleration or negative acceleration, but just to be clear, we really don't have different words. In fact, this is also something that probably I should have written down. Maybe you should. Like this becomes really important to note. It's really important to note that acceleration is a vector, because from here on in, we're not going to distinguish it from scalars. Like we're really going to be in equation land from here on in. Put another way, you notice displacement was built off the word distance. And velocity was like built off the word speed, but there aren't 2 words like that for acceleration. There's only 1 word. Okay, that's where, so we really start getting into physics here, and we really start having to trust ourselves that we know the context, because there are not 2 different words for acceleration. The way that like acceleration in physics always means that concept that measures, that measurement that includes both magnitude and direction. So anytime, so if someone has acceleration, that might mean they're speeding up, it might mean they're slowing down, or it might literally just mean they're turning. And what do all those 3 things have in common? Why are they all described by the same word? Because all 3 of them is what you would feel. That's that, right? Like in an airplane, for example. Okay, so that's number 1. So you have a non-zero acceleration as long as you're doing any of those things. Now, to be sure, like sometimes you might have a negative acceleration. And it might be easy to think, oh, I get it. Okay, fine. These physicists, they use positive acceleration to mean speeding up, I guess, and they use negative acceleration to mean slowing down. Well, it's not that simple. It's not that simple. If you look at the equation, and we're going to start practicing it in a minute, the equation says average acceleration is change in velocity per time, i.e. difference in velocity, right? Change difference, like one velocity subtracted from the other, which then means sometimes we're going to get positive signs from that. Sometimes we're going to get negative signs depending on which one was bigger. But so that means we're going to have a negative, like we're always assuming that one direction, we're still living in number line here. We're still in one dimension of space in this context, so in this chapter of physics. So we're still picturing that number line, like at the front of the classroom that someone's going back and forth along. And like, that's the only degree of freedom they have, is whether to go back or forth, or north or south or forward, or whatever you want to call it. But it's just that one axis, right? And so all of this assumes that we will have previously designated that one direction in that axis is positive. Like all the numbers to the right of 0, let's say, we might say, are positive, and then all the other numbers to the left of 0 are negative. Now, we could say anything we want. We could have flipped that. We could have done it the other way. But once we make it, it is up to us. But once we make a decision, then we stick with it. And by the way, maybe you're starting to see now, why is it up to us in the first place? Why do we both get to make that choice, but why also do we have to make that choice? Because velocity is relative, because everything is a comparison. Everything is based on what you choose to be your reference frame or your reference for comparison or your base of comparison, like because velocity is relative, because there is no objective coordinate system in the universe, right? This is all tied together. There's no, it's not like the Earth is or is not actually the center of the universe. And it's not like the revelation of Galileo would say, oh, we thought the Earth was the center, but we're so silly. We thought the Earth was the center, but it's actually the sun. Okay, now we can do physics correctly. The sun is the origin of our coordinate system. Let's go now, people. No. What Galileo is saying is, no, there is no objective origin to any objective coordinate system in the universe. Every coordinate system is a comparison to every other coordinate. So anytime we do an experiment or data collection, we choose what our base of comparison is going to be. We choose our frame of reference. Okay, right? I mean, I think you're getting that. And once we do that, once we say, fine, in this axis that we're looking at, in this number line, all the numbers to the right, we're going to call positive. Like anything going to the right, we're going to call positive. And anything to the left, we call negative. Okay, then, once we make that distinction or that designation, then a negative acceleration would mean, and again, you might see this more concretely when we start running the numbers, but a negative acceleration would mean the velocity numbers are getting lower and lower. Right? Like negative acceleration means you're losing velocity. Okay. Sounds like getting slower to me. Well, could be if you are moving in the positive direction. If you're moving to the right, like if you had a positive velocity of 35, and then a little bit later you have a positive velocity of 25, then sure, like it's like 25 minus 35, like the now velocity minus the earlier velocity, 25 minus 35, you get negative 10. So yeah, your velocity numbers are going down, so you get a negative. So it's like, yeah, it was slowing down while I was moving in the positive direction. I got a negative acceleration. But what if you're traveling in the other direction? What if you just happen to be not doing anything weird, but you happen to be traveling to the left, where your velocity numbers now are negative numbers, right? Because that's what we learned at the beginning, that a negative velocity just means going that way rather than going that way. So if you happen to be going that way and your velocities are negative, and say like you have a negative 25 velocity, and then a little bit later you have a negative 35 velocity, i.e. you're moving to the left, speeding up, well, your velocity numbers still went down, right? If you're moving negatively, but speeding up, your numbers, they didn't get decreasingly positive, but they did get increasingly negative, right? And what would that be? That would still be a negative acceleration, is what I'm saying. Like if you understand that positive 25, and we'll see this when we run the numbers, but if you understand that positive 25 minus positive 35 is negative 10, so that if you understand that a negative acceleration means slowing down, in that context, then I'm here to say it means slowing down as long as you were already moving in the positive direction. If you're moving in the negative direction, then negative acceleration would mean speeding up. Because negative 35 minus negative 25 is also negative 10. Negative acceleration either can mean slowing down while moving in the positive direction, or equally well can mean speeding up while moving in the negative direction. Just please take note of that. Even if that was too much or too abstract, or you're like, can you show me the freaking numbers? Because that was too, then fair enough, and I will, but it just at least take a note of the fact that there's a such thing as negative acceleration, but it's not maybe as it doesn't necessarily mean slowing down. And you'll see, that's what I'm trying to say. So we have to be careful. Acceleration's a vector. That's the bottom line. Let's start using it for real. We've got 17 minutes. Let's start doing homework for and applying it. And let me see. I'll screen share. Yeah, I'll screen share and then you can screenshot. All right, so I'm going to screen share for a second. Sorry, just so you can see what I'm talking about. I mean, presumably you guys in the class like have homework 4 maybe in front of you. Hopefully, I don't assume that you've started it, but hopefully you have it. But just so we all know what we're talking about here, I think it's right here. Yeah. Okay. Right. Okay. So this is homework 4. Right. Oh, Professor Bean. He's no longer with us. Oh, he's in Chicago. Hello, Professor Bean, whoever you are. I know you once subscribed to this channel. Anyway, we missed Professor Bean. Okay. Okay. Maybe I can even write right on this. Yeah, I think I can. Hold on a second. So question 1 is a very quick review. And really, the whole point of question 1 is it doesn't even say anything about acceleration, right? It doesn't even say anything, but what it's doing is forcing us to remember that how much we have to care about direction and coordinate systems from here on in, because all these quantities are vectors. Let me see if I can write on this. I think I can. Okay. If you were doing this homework, say like you're a student and you're handing it to me, this is a very good example where even though I didn't provide one, absolutely you should provide a diagram before you do anything at all. Provide a diagram. It could be a very simple diagram, so simple that I'm not even going to do it well. A very simple diagram, and do it on a separate piece of paper, of course, please, but I'm just going to do this here so you can see. You must provide a diagram first. And what's the point of your diagram? You might think, well, what is their diagram? The thing to diagram is what you're calling positive and what you're calling negative from here on in this. So how can I do this? Can I do this? If I can't, I'm going to unshare in a second. But oh yeah, okay. Now, this is a horrible, obviously. Now, again, partly this is horrible because I'm doing it right on the page, which is exactly why I tell everybody don't do it right on the page. I'm doing this here so we can all see it together at the same time. But notice, before I do anything, I am making a coordinate system explicit. I'm saying something that is a choice. You might even think it's an obvious choice, but it is not the only possible choice. I could designate south to be positive, and I could designate north to be negative, and I could get all coherent answers, because velocity is relative, okay? But in order to get coherent answers and answers that make sense, I do have to make some kind of choice. So here's my choice. I've made a coordinate system I'm living. I'm saying from now on, anything that's in the north direction is positive, and like I'll show it up the page, and anything that's in the south direction, I'm gonna call negative, right? And if, okay, now with that designation, and I'm going to give you answers here. Like, hopefully it'll help everybody. But again, please forgive me for the fact that I'm writing directly on the page. I think it's, oh, it even says draw a picture. Yeah, okay. Okay, so now I'll try to, oh wait, I could actually type, couldn't I? Hold on a second, I'm sorry. It's like, and then man discovered the computer. Okay, this is not meant to be a trick. Okay, I mean, and again, if you're in my class, like show a little bit more work than this, but there's not that much work to show. Maybe just give a definition first of distance and then give the answer. But I'm just saying, I'm just trying to show you there's not meant to be a trick here. We always do this in physics. We ask sort of comparatively simple or self-evident questions first, and then we're going to base the further answers and further explanations on those initial answers. We always want to go in the order of like a proof, from the most self-evident to the least self-evident, so that we believe what it is that we're doing. So anyway, I mean, so Berlin is like 700 miles. And by the way, in my diagram, I probably should put like a Berlin and I should put a Rome. Again, I'm just like cramming this in so you can all see. But if Berlin is 700 miles north of Rome, and a woman flies in a straight line from Berlin to Rome, then the total distance that she flew was 700 miles. And the whole point of question A is it doesn't matter whether she flew north or south. If we're just asking about distance, it's 700 miles. But then B B, according to my coordinate system, right? According to my coordinate system, anything north is positive, anything south is negative, and she flew from Berlin to Rome. So she flew south. So according to my coordinate system that I just drew, and this actually is almost worth noting, and I'm sure you don't find this hard. I mean, I hope you don't find this like too weird. It's not meant to be tricky. Again, it's almost review, but do notice this. Like, and I should circle these answers, but I'm not because I'm like being computer incompetent. Could I also recommend, again, Gus Johnson's YouTube video on how to be a professor? Absolutely hilarious, absolutely savage. I mean, he shows a professor in front of a computer, like a computer and an overhead projector, and the professor is totally incompetent, and it's like completely accurate and hilarious. But anyway, what I'm saying here is no. I made what seems like, I mean, I guess this is a part of the point of the diagram. You might think it's like totally obvious, like north is positive, south is negative. Of course, like why do you even have to waste time saying that, Yaverbaum? But here's the thing. It's obvious only because it's a common choice. It is a common choice. And right away in this problem, to be frank, if you see right away, it's actually kind of an inconvenient, dumb choice for this problem. I didn't even look ahead and read ahead when I made that choice. I made the common choice of north being positive and south being negative. Now, there's nothing wrong with that. And now that I've written it down, I can use it. But the fact is, I just made a choice that ends up making the basic fact of the problem negative. That's not actually convenient. If nothing else is going to happen in this problem, like I don't want negative signs in my life just for the sake of them. We use negative signs when we have to. We kind of want to minimize the use of negative signs when we don't have to. Like, honestly, it's generally you want to make a choice in physics where you have as few negative signs to deal with as possible. I just made a choice that ended up making my basic fact of this problem negative. Now it's correct. My answer is correct, B, but it's correct based on the diagram and the choice I made. If you make a different choice, a wiser one, and you decide to say, you know what, everything in this, I'm reading ahead and everything in this problem is all going to be going south, you might as well call south positive, and then all your answers will be positive, and you will be correct. And this is finally, I know I'm like over talking this point, but the harder things get, the more important this is. This is the reason the diagram is so crucial, that I actually can't grade these answers, or like these answers are meaningless except in comparison to the coordinate system that we chose. In other words, some of you might write positive for B, and some of you might negative, and you get credit or not, depending on whether it's consistent with the choice you made. I honestly can't say whether 700 is objectively correct or negative 700 is objectively correct. It totally depends which direction we've designated previously as negative or positive. You see what I'm saying? Right? Okay. And then we have to stay consistent with that choice. But anyway, with that choice, so everything is relative, excuse me, not everything, but velocity is relative. These are the implications of the minute we say that the Earth is moving, we have to be careful about all this crap. That's kind of what it comes down to. All right. Anyway, so those are the answers to that. Then I'll give it time. All right. Then and stop me if I'm just trying to get things done for you, with you. But please do stop me or you can always write in the chat. Please speed up. You're killing me. I wouldn't be insulted. I mean, I would cry like all night, but like I would understand and I would accommodate. So see, what's the average speed for this journey? Maybe I should even ask you guys. I should, but oh, that's the other thing. You know, if I'm going, maybe you don't want to write in the chat, please speed up, because maybe you don't want to hurt my feelings, but feel free to start putting answers in the chat if you want. If you think you know the answer to C or D, really, like rock, I mean, you'll get points no matter what, right? You'll get more points if the answer is wrong, oddly. So feel free to speed me up or to show me that I should speed up by putting things in the chat. I'm about to do C here because it probably takes me longer to type than it takes, well, it certainly takes me longer to type than it takes you. So, but C, and again, if you're doing the homework, you don't just write the answer, write the equation first, the definition first, and then, do the steps. But anyway, I just can't share that many screens at once. So C, what is our average speed for this journey? Well, average speed, okay, I'll try to do what you should do in the homework. What you should do is say, first, general definition or principle. Average speed is defined to be, now I should do a triple equal sign here. I don't think can I do a triple equal sign? Wait, I bet I can. Well, this would be impressive if I can. Hold on. no, that's not what it said. Oh, yes, yes, yes. Okay. Oh, it didn't work. Sorry. All right, I can't do that. Now I messed myself up. Now I'm Gus Johnson. No, I'm not Gus Johnson. I'm not that cool. I am the guy that he made fun of. Can I? Well. Okay, again, I should circle the answer or whatever, but you see what I'm doing, right? So the answer to C is 175 miles an hour. There's no positive, there's no negative, because it's asking about speed. I've put first technically the definition of average speed. It should be a triple equal sign there, but equals distance over time. So then I, right? So that's like step 3, general definition or principle. Then I apply to the particular problem. Here, the average speed, I plug in the numbers. Here, the average speed is 700 divided by 4. So I reduce. Okay, so the answer is 175 miles per hour. I think you get it. You can totally stop me if you don't. Oh, chat. I'm sorry. Oh, chat. Yes, awesome. Daniela. Yes. So she gets a million bajillion points for doing that. The only point she doesn't get is the points for being wrong, sadly. Isn't that weird? I have to do something about that. I know that's very weird. And now she's speeding it. Now I'm shamed into going faster. Very good, Danielle. Awesome, obviously. And you should put those as separate entries for separate things of points. Awesome. I totally agree with her. Okay, I'm going to speed up because obviously at least one person is with me. She's totally right, Danielle, and I'm totally psyched that I'm not killing people with boredom. Well, maybe, actually, I guess that means I am. But so C, she got 175 miles an hour, totally right. And then D, she's saying now we're talking average velocity. That's displacement over the time. The displacement was negative 700. So yeah, I'm not even going to, actually I am, because you can't see. I'm just going to put it here for completeness sake, but she's absolutely right that the answer to D is negative. That V bar, and I can't put a bar over it, so I'll go like this. Average velocity equals negative 175 miles per hour. Okay, so and that, that's D, sorry. So those are the answers. Those are the answers for one. Again, that's like very like sloppy and horrible, except for Daniela's part isn't. But just so you know, we're on the same page, and just to also reinforce, it's not supposed to be a trick. They're just supposed to establish some basic things to help us with the rest. And let me scroll up. We've got like 3 minutes. Okay. Notice, well, okay. That's so strange how the writing is transparent to the scrolling. I'm sorry, I don't even know what to say about that. But so now we go to instantaneous velocity. Yeah, we only have 3 minutes, but now I have to say something about this. The answer, this question says, okay, 2, instantaneous velocity. Note, we have not yet established a method for computing instantaneous velocity. We have not yet. All of a sudden, there's another concept being thrown right in the middle of the sheet here. Okay, what's actually happening here is we're actually now introducing a word to refer to something that I've been tacitly saying for the last hour, but haven't actually admitted it. The key point right now is that we believe it exists and can be computed. Like what? What exists? What can be computed? What am I saying? What I'm saying is this. Oh, wait, is that a question? Oh, no, that's mine. Okay. What I'm saying in the 2 minutes that we have left is, remember I said that we have this new equation, average velocity, A bar, triple equal sign equals V minus V naught over T. And on the right side of the equation, we're a V and a V naught. And it makes sense. It had the same structure as V bar equals X minus X naught over T, right? We're saying that an average change in acceleration, we're saying an average acceleration is a change from one velocity to the next in time. So in the right side of the equation, we suddenly were writing V's for the first time in this class. I kind of like slipped it in there without saying it, but we were suddenly writing V's without bars over them. We were just, and it didn't bother anybody maybe because it's like, okay, yeah, V with a bar over it meant average velocity. So suddenly on the right side, we're just writing V's without bars. So presumably everybody just sort of like, didn't like jump on me and we're like, okay, I guess V without a bar is just regular old velocity. Well, yes, that's correct, but except for the regular old part. V with a bar is average velocity. V without a bar means velocity at a point in time, right? Like that's what that we're in that equation that we're just now all using now. We're saying average, and I know I have 1 minute, but average acceleration equals change from one particular velocity, like a velocity that occurs at a particular point in time, to the next velocity. Like it's not averages now we're talking about velocities at a moment. That's what V and V naught are, V's without bars over them. Now, strictly speaking, those are called instantaneous velocities. That's not average velocity. That's an instantaneous velocity, a velocity at an instant. And what this question is just pointing out is, okay, from here on, apparently we have that concept. Like, I'm sure you can picture it in your head, like not how fast did you go over time, but how fast are you going right now? Like what the cop pulls you over for. Do you know how fast you were going right then when you passed the school zone? That's what we're talking about. V without a bar over it is instantaneous velocity. It is what you're picturing it to be, but I have to establish right here and now, in class it's like over. But as a physicist, we may have that concept and we may not have that word and we have that symbol now, V without a bar over it. But we haven't actually established any way for computing that or any equation for that. We don't have an equation or even a definition really or a concept for instantaneous velocity. We only have an equation for average velocity. However, this question is here to raise the idea that that doesn't mean, just like you can already picture it in your mind, it's what the cop pulls you over. In certain scenarios, I bet you can even figure out what it is. Maybe not in all scenarios, but that's what we have to develop in the next class is this, how to get instantaneous velocity and relate it back to acceleration. So I'll tell you the answer for 2. I'll tell you the answer so you don't overthink it or think it's a trick. The answer for 2, but be careful, but the answer for 2 is 80 miles an hour, 80 miles per minute. It is what you might think. The answer for 2 is 80 miles per minute is the answer, but you really want to think about, like, make sure you understand why you believe that. I'll stop right there. You've been very patient. I'm going to stop the screen share too. You can go. Goodbye. Thank you. But if there's any questions or whatever, I'm right here. Let me just stop this to share. And I'll stop there. Oh, good job, Daniela. Thank you. Oh, and thank you, Vivian. Thank you, Noel. Thank you, Alyssa. Thank you, Daniela. Bye. Okay. Thank you so much. Okay, cool. I think everybody. Sorry. Okay. Okay, thank you. Oh, that's everybody. Okay, that's everybody.